Hello, 5.09, 5.011, liquids and stuff. Okay, so 5.09, liquids and vapors. Evaporation is when some particles in liquid move faster than the others near the surface, and they are able to escape to form a gas. So for example, like the sun, the radiation, it comes over, hits one of the particles freaks out like, oh my god, the radiation hit me so hard. And after that, like, okay, screw this, I'm out of here, and then it flies off. That's basically what evaporation is. And it happens to every single liquid at every single temperature because of radiation, heat, whatever. And it only happens on the surface, mind you that. Evaporation can be sped up with increase in temperature, increase in surface area, reducing the humidity, and blowing air on the surface. So increasing the temperature is pretty self-explanatory. So if you increase the temperature, it'll increase the amount that the particles vibrate, therefore they have a higher chance to escape their relatives' molecules. And increase the surface of area. Now if you increase the surface of area, it will increase the surface area so that they could receive more heat and they could receive more radiation so that they could gain more temperature, therefore increase energy. And also it could increase the surface area to blow air on it. We'll get to that. Reducing the humidity. So if you don't know, the definition of humidity is the amount of water in the air. So if there is a lot of water in the air, then that means that the water will have trouble going up into the air because they're like, they're freaking out, so they want to go out into the air, but they look up and they're like, oh man, there's already air, like water particles up there, so maybe I should just stay down here. And then but this problem can be solved with blowing air on the surface. If you blow air and it's humid, then all the water molecules will get carried over by the wind, and so all the water particles get moved over, and then the water particles on the surface, they're like, oh, now there's space, so I can go up there. So they go up there and they're all happy and being a gas and stuff. And yeah, that's did I want to say something? Humidity? Never mind, I forgot. Okay, boiling. It is a rapid form of evaporation, but it happens throughout the liquid instead of just the surface. Yeah, don't get confused with boiling and evaporation. They are not the same thing. Boiling happens throughout the liquid, and evaporation happens only on the surface and at all temperatures. Boiling happens only at specific temperatures. We'll get to that. And also, it only happens at high temperatures, usually. Except when you're dealing with gases, when their boiling temperature is quite low, actually. So, water bubbles inside of water expand and rise to the top to burst and release water vapor. So, inside water, you can't really see it, but there is water. There is air particles inside there. If I have a water bottle right here, I'm shaking it, and you can see some of the air, it flows up to the top rapidly. But as you can see, if you look really closely, there is actually smaller air particles flowing up to the top. And yeah, it's really small, but when you supply heat, the air expands and it flows up way faster because, I talked to this before, it decreases its density, therefore it floats to the top. And when it floats to the top, it takes up some water with it and it releases vapor. So that's how boiling works. That's why it's so fast, that's why it's so rapid, that's why it's so efficient, and why we use it to make steam. How can we take advantage of evaporation? When evaporation happens, it carries away heat in particles that turn to gas, cooling the liquid down. We actually use this without realizing. We sweat to release water, so that when it evaporates, it carries away heat, cooling us down. This is also why it is hotter when it is humid, and this is why we are more comfortable under a fan. So I'll explain the first point. When evaporation, it carries away heat in the particles that turn to gas. So on the surface, it's very the particles vibrate quite fast, and this is heat. When they're heated up, it vibrates really fast. So when it escapes, it takes away some of that heat from the average, all of the whole thing, from the whole liquid. you take out a little bit, then the average goes down. And you take out a little bit more, the average goes down. And the average is actually what the temperature we're measuring is. Okay. So sweat. We release sweat from our bodies, from our pores, and it releases out, and then after that it evaporates. When it evaporates, it carries away heat, and that heat helps it, and that heat carried away makes us cool, and yeah, that's why we sweat when it's hot. Our body's response to, oh no, we're getting a bit hot, we should cool down. This is also why it's hotter when it's humid. So when it's humid, right, I told you before that it's harder for evaporation to happen because there's already air in the surface, in the air. So the air is like, maybe I shouldn't go there because there's already air there. So, yeah, it's humid, and so we have trouble sweating, and therefore, like, the heat stays on us. But when the heat stays on us, we sweat more, but then the sweat won't evaporate and take away the heat, so we sweat even more, and that's why we sweat a lot when it's heated. And this is why we're more comfortable under a fan. When it's a fan, like before, increases the rate of evaporation by blowing air on the surface, moving the humid air with air particles away. So therefore, you can get space so that the water from your sweat can evaporate and carry away the heat. This is a fun fact. Sweat, it actually contains salt. If you've ever accidentally or purposely for some reason licked your sweat, it tastes like salt. And the reason for this is that when you add salt into water, it decreases the it decreases the temperature it needs to evaporate. There's some fancy science behind it. I think it's in chemistry, or I can't remember, but yeah, that's what happens. You add salt, it decreases the temperature from liquid to gas, and yeah, it helps cooling us down. Refrigerators. In the fridge, there are pipes filled with liquids called refrigerant that can transfer heat efficiently. The expansion device is right there next to the fridge. It turns the liquid into vapor. It requires heat to turn the liquid into gas, so it takes in heat from around it, cooling the fridge. So like it uses pressure, I think. It uses pressure to turn the liquid into a vapor. So it decreases the pressure, therefore it turns into a vapor. But then, like, you need heat to turn water into vapor. So then it absorbs heat from around inside the refrigerator, cooling it down. It flows back out. Here. The expansion device turns the liquid into a vapor. I'm here. The vapor goes into a compressor that turns it back into a liquid, which releases heat that is dispersed through heat vents at the back. Yeah, so it goes through, it cools down the refrigerator, goes all the way back down into the compressor. Compressor's like, okay, turn back to a liquid, so it compresses it back down. But then when it's compressed back down, it doesn't need that heat anymore, so it's released. So it flows back out here, and it releases heat through these vents, these coils. The reason why they're tangled up like that, all these places here, is to increase the surface area that they release the heat or absorb the heat. Oh wait, hold on. Refrigerators, they're similar to air conditioners actually. You can actually find the same sort of system inside air cons, except that the tubes are longer and this condenser is at the back, is outside. That's why you see those those big fans at the back, those big boxes, and then it goes inside, and the inside is actually what is the aircon. Condensation is when a gas turns into a liquid. This happens in clouds. Water vapor gets heated up, floats up, and then it cools down. The tiny water molecules form. These are clouds. So yeah, water flows up, gets cooled down, forms clouds. What more can you say? Up there is much colder. This also happens when you have a hot shower. The vapor touches the cold mirror and cools down and becomes liquid. Mirrors are naturally colder than everything else because they are good emitters. Right? Wait, no. They're not good emitters. They're great reflectors, that's it, so they don't get heated up in the first place. Specific heat capacity. I don't like this topic that much, neither like the next one. So what is heat capacity? It is the amount of energy required to increase the substance temperature by 1 degree Celsius, and or Kelvin, if you want to use Kelvin like a noob. But specific heat capacity is the amount of energy required to increase 1 kg of a substance temperature by 1 degree or Kelvin, if you want to be a noob. So if you add specific in front of heat capacity, then it just means you need to add the mass into consideration. Yeah, that's the difference. So for example, over here is like, here's a blob of aluminium. We don't really care, but how much energy do we need to turn it into 1 degree? Yeah, we don't care how much it weighs. We just need the energy, the heat capacity we need. But over here, there's the mass, and this is exactly 1 kg, and we know that it needs to be this much energy to increase by 1 degree. That's what it means by specific heat capacity. The equation for energy transfer capacity. Just ignore the capacity. The energy transferred is Q equals MC. I forgot what I think it's called. Triangle T, but the triangle signifies temperature change. Just that thing is change. Okay. So energy transferred is measured in joules, mass of substance, obviously in kg. Specific heat capacity is in joules per kg Kelvin, or degrees. Kelvin if you want to be a noob. Alright. Thermal capacity. Thermal capacity is removing the specific out of the equation so that it is 1 joule per kilogram per degree, and we are dealing with 2 kg blocks, so we just multiply the specific heat capacity with the mass, and so you get the HC, or the heat capacity, or the thermal capacity. Thermal capacity and heat capacity are the same thing. So for example, there's this 1 kg block, you want to know what's the heat capacity for it, but then you also want to find out the 2 kg block. And then, so you find out the first one, and you can already find the second one because it's just multiplying the mass by 2. Oh, okay, latent heat. I have to go really fast because I actually ran out of time. Okay, what is latent heat? Latent heat is the energy required to turn solid into liquid to gas. Specific latent heat is like before, like mass. How much energy is required to turn 1 kg of solid into liquid, or liquid 1 kg of solid into gas? So 1 kg of solid into liquid, and this energy that is required, that is what latent heat is the energy required to turn solid into liquid. Energy is measured in joules, keep that in mind. It is heat required to turn 1 kg of solid into liquid. Fusion is from solid to liquid, just keep that in mind. Keep that in mind that the temperature stays the same while turning into different form. You see here, it keeps rising up, and then it stays the same for a bit, and it rises up some more. The reason that it stays the same right here is because instead of using the energy to increase the temperature, it uses the energy to break the bonds between the molecules. So it's like, hey guys, we reached the melting point, guys. So then they're like, okay, start separating, and then they start separating, and that's why they use the energy to break the bonds instead of increasing the temperature. Equation: energy transferred equals to mass times specific latent heat. Energy transferred is actually the energy required to melt something, or to heat up something, to evaporate something. This can be used when trying to figure out how much energy is required to turn ice to water. So solid to liquid is 80 calories. I don't know why it uses calories, but in the book, if you're curious, it uses 330,000 joules to turn 1 block of ice into 1 kg of water. Latent heat to vaporization. Energy is required to turn liquid to gas. It usually uses more energy to turn to gas. So I have like 50 seconds left of recording, and I'll use that to explain vaporization. So vaporization is basically just turning water into gas, or any sort of liquid into gas. In the book, it uses 2,300,000 joules to turn 1 kg of water into 1 kg of water vapor. It uses more energy because gases have barely any attraction. You know what? I'm just gonna end it there. Okay. Thank you very much for listening and bearing through 15 minutes of me talking slow and then speeding up at the end. Okay, thank you.